Hi there, algebra students. We're going to practice writing expressions, and we're going to concentrate on two types with this review, linear expressions and exponential expressions. But in all of these expressions, there's a strategy that kind of comes through whenever we're dealing with linear or exponential stuff, and that's that we have to look for, I'm going to make my pen just slightly thicker here, we have to look for where it starts and how it changes. And that's going to help us out with exponential and linear stuff. So let's go ahead and start critically reading this thing in order to try to figure out. I've got my highlighter ready to find some important stuff. Dolly Parton started her Imagination Library initiative many years ago. In the program, a child is sent a new book every month until their 5th birthday. That's 60 books, and it's totally free. Henny, Mr. Bostwick's daughter, has already received 33 books, so that seems important. And so does that 60 books that they get total. Write an expression that shows how many books Henny has left to receive. And so if I'm thinking about how many books Henny has left to receive, that means that it should be decreasing because she gets a total of 60 books, and so it should be decreasing. So I'm just doing some thinking, so I'm going to just make a note to myself, decreasing. All right, so where does it start? Well, she's already received 33 books, and she gets 60 books total. And so I think those two pieces of information kind of tell us that if I take 60 books minus 33 books, that's going to give me, I'm going to do my calculation here so I don't make a mental mistake, 27 books left to go. So 27 books left to go. And so now I need to figure out how it changes. And so she receives a new book every month, and I'm supposed to figure out how many she'll still have after a given number of months. So really it's like the number of books she has left to go should decrease. That's subtract one book per month. And so she's got 27 left to go, and she's taking away one book per month. And of course, we always have to tell what our variable is. The m here is number of months, and we can get super precise from now. And if you're thinking about it, this here, since we're taking away, since the subtraction pattern, this means it's linear, and so our rule should be linear as well, which it certainly looks that way. All right, so that's a linear expression. So let's kind of try to use the same model and notice something different when we consider an exponential expression. So I'm going to jump all the way back up to the top of my list here. So a little bit of science for you. The basic reproduction number of an infectious disease indicates how quickly the virus or bacteria spreads in the population it is infecting. The common flu has a basic reproduction number of 3, so I'm getting my highlighter out, because each person with the flu will infect 3 more people. Pertussis, so I'm going to write each person with the flu will infect 3 more people. Pertussis, which is an infection of the lungs, has a basic reproduction number of 16. Write an expression to represent how quickly the virus will spread at progressive stages of infection if there is currently 1 person at BHS with pertussis. Pertussis is also called whooping cough, so I'm going to use the same thing here. How it starts, how it changes. You might think how it grows or whatever, but sometimes things decrease, so I like to use changes to kind of get a little bit more general. And so how it starts, well, it says right here there is currently 1 person at BHS with pertussis, so 1 person with pertussis. 1 person with pertussis. Sorry about my sniffles, I got some allergies today. And now we're going to think about how it changes. So here's how it changes. It says if you're thinking about the flu, each person with the flu will infect 3 more people. So if you recall in your class, if you have 1 person with the flu at stage sort of 0, they're going to infect 3 people, right? And so now 3 people have the flu, and that's at stage 1, so 3 more people get infected. Now each of those people, 1, 2, 3, 1, 2, 3, 1, 2, 3, is going to infect 3 more people. And so since it's each person who's infected infects 3 more people, we get this multiplication pattern. So if I'm writing this, this is 1 and then 3 and then 9. So I have times 3 and times 3. And so that's for the flu, but I am analyzing pertussis here. And it's going to be really hard to make a diagram for it, and that's because it has a reproductive number of 16. And so each person, I'm just paraphrasing here, which is a helpful thing for you to do whenever you're confused about a problem. Each person infects 16 people. It's an incredibly infectious disease. Okay, so each person infects 16 people, and so I'm going to make a little table for this too. So I know that one person has it right now, and I know after one stage that person is going to infect 16 people. And now each of those 16 people is going to infect 16 people. And just like before, that was a multiplication pattern. When we had each person infecting 3 people, it became a multiplication pattern. It's going to be a multiplication pattern this time. And so 16 times 16 is, I think, 256. And then we're going to multiply by 16 again. And again, I'm just processing here. You don't have to make a table for all this stuff, but it's often really helpful when you're trying to write these expressions to kind of see what's happening. And so each person infects 16 people tells us that it's changing by multiplying by 16. So I'm going to write that up here, times 16. And so when I see a multiplication pattern, I should think, well, that's exponential. And when you think about exponential expressions, you have to think again about, I'm going to do a different color so it kind of stands out here. It starts at 1, because one person has it, and that's right here as well. It starts at 1, and then every stage it's going to multiply by 16. And because we're multiplying by 16 over and over and over again, we're going to multiply by 16 to the x, where x equals the number of stages. And so that tells us that we start at one person, and it changes by multiplying by 16 each time, and the each time is kind of right up here. All right, so that's one exponential expression. It's kind of a difficult one. So one of the things you can think about is that if each person with the flu will infect 3 more people, that's going to be a phrase that tells you it's a multiplication pattern. Let's try one more of these just so you have some more to go with. All right, so this one says, "Holy sharks, you were preparing a gourmet meal for your sweetheart when you were jovially julienning a zucchini you sliced into your finger. Because of the reprehensible state of your kitchen, your cut became immediately," that should say infected. I guess affected is okay as well. "The number of bacteria in your cut is doubling every 15 minutes. So I'm going to do some highlighting. Doubling every 15 minutes. You have 376 bacteria in your cut now. So I'm going to go back to my model here. Starts, changes. So it starts with 376 bacteria. And it tells me it's doubling every 15 minutes. Well, doubling means every 15 minutes is going to multiply by 2. All right, so let's think about this. I've got multiplication by 2, and I start at 376, so I'm going to multiply by 2, and because in this case I'm going to multiply by 2 every 15 minutes, I'm going to multiply by 2 to the x. And x is going to be a little bit difficult this time. X is the number of 15-minute intervals. Because every 15 minutes it doubles. So that's another example. You're looking for phrases like doubling or something like that to tell you that you're dealing with a multiplication pattern. I hope this has been helpful. Thanks for watching.